Good evening, good afternoon, and possibly good morning, everyone. My name is Kyoko Marumo Suzuki. I'm the head of the Science and Technology Office of the Embassy of Switzerland in Japan, and it is my great pleasure to be the moderator for the EPFL Virtual Space Tour, the first day of the 4-day series to showcase the wonderful projects and research from EPFL, the Swiss Federal Institute of Technology in Lausanne. We have a wonderful program connecting Japan and Switzerland with people at the venue and also online. And therefore, I would like to keep my comments short. But since we have many online participants, I would like to share with you just one housekeeping rule. Please kindly stay muted during the event and make sure your Zoom profile states full name. And then if you have any difficulties, please let us know using the chat function. So without further ado, I would like to welcome Mr. Markus Reubi, Chargé d'Affaires AI, Embassy of Switzerland in Japan, for the grand opening remark. Mr. Reubi.
Thank you very much. Dear distinguished guests, it's my great pleasure to host the EPFL Virtual Space Tour, a tour which is organized by EPFL Space Center and the Science and Technology Office, Tokyo, here, hosted here at the Embassy of Switzerland in Japan. The hybrid tour marks also the launch of two very important projects. First of all, the virtual escape game Tranquility base, and secondly, the newest edition of the virtual reality universe project called VIRUP. These two projects by EPFL, the Swiss Federal Institute of Technology located in Lausanne, highlight how Switzerland is successfully promoting science communication and public engagement. This has become increasingly important for many countries, including Switzerland. Why is this so important? I think science communication is valued not only because scientific expertise is playing a more crucial role for many individual, organizational, or societal decision makings, but also because science and research rely on public acceptance and social legitimation. We see this currently today also when we look at the role of science in the fight and science and research in the global fight against the COVID-19 pandemic. Furthermore, science communication is a means to enhance excellence in education, research, and innovation, all of them being sources of prosperity, of national prosperity. Let me also highlight that science communication contributes to the achievement of the Sustainable Development Goals of the United Nations, more particular of SDG 4 and SDG 9. SDG 4 tells us that ensure inclusive and equitable quality education and promote lifelong learning and opportunities for all is to be reached by 2030. And SDG 9 sets the goal to build resilient infrastructure, promote inclusive and sustainable industrialization, and foster innovation. So really contribution to national prosperity for countries like Switzerland and Japan, and also contributing to prosperity on a global level. In light of such significance, the Swiss Academy of Arts and Sciences has published its first very comprehensive assessment report on the science communication in Switzerland. It's, I think, available online for those of you who are interested. Please take a look. It has been published in July of this year. For these reasons, the EPFL projects are truly meaningful. And I'm so pleased to learn more about these projects from the creators. And the two creators which I would like to mention here and which we will hear from are Mr. Florian Cabot of the Laboratory of Astrophysics at EPFL and also Mr. Alexandre de Montelau, the new president of the Student Association Space at Your Service. Last but not least, I would also like to add that I'm looking forward to listening to the special lectures and speeches of Professor Masahiro Takada of the KAVLI Institute for the Physics and Mathematics of the Universe, and also of the University of Tokyo, and also Professor Jean-Paul Kneib, the director of eSpace at EPFL. So with all this, I wish you a very pleasant evening and please enjoy the event. Thank you very much.
Thank you very much, Mr. Reubi. And now it is my pleasure to invite Professor Jean-Paul Kneib, Director of EPFL Space Center eSpace, who has organized this event. Professor Kneib.
Hello, can you hear me? Yes. I'm really pleased to be with you. I mean, I would have be even more thrilled to come to Japan for this event, but sadly the conditions are not possible to do this. I'm very pleased to be Ron, and maybe I'll explain a little bit very quickly what I'm coming from. I'm a professor in astrophysics at EPFL. My main interest is observational cosmology, understanding the universe, and I'm doing that with different techniques, and we will see that during the presentation. The lensing, the mapping of the universe in 3D. And to do that, I'm using telescope. I'm also developing instrumentation to enable this observation. I'm also leading the Swiss SK project. That SK is a radio astronomy project that will start in a couple of years in South Africa and Australia. It's an international project. I think Japan is also interesting to join this project. And I think it would be the next big window of opportunity to discover more of the universe. I'm also, as it was mentioned, director of the EPFL Space Center. At the EPFL Space Center, we're trying to develop innovation in terms of space, and more particular, clean space, sustainable space logistics. We are also willing to connect with situational space awareness, knowing all the satellites and debris that are orbiting our Earth. And this is also by using astronomical telescope. We have a strong program in education, which is essentially bottom-up in terms of the projects. We encourage master student and bachelor student to develop projects, and some of them are participating to this event. Altogether, there's about 300 students working in six different teams at EPFL. And I can mention the Moon Analog mission, the rocket team, the spacecraft team, the Grub team. So there's a number of projects at EPFL mastered by students that will eventually develop into startups or developing into new research. So welcome to this event. And I'm sure you will be interested to what we're gonna show, and maybe I'll leave the floor to the next person.
Thank you very much, Professor Kneib. And now, today only, we have a special remark from the head of the Swiss Space Office, Mr. Renato Krpoun. Mr. Krpoun, thank you very much for joining us today. The stage is yours.
Thank you very much, and good afternoon, ladies and gentlemen. I'm delighted to be part of today's event and have to apologize for tomorrow. Unfortunately, I will not be there. But today's event to inaugurate the EPFL Virtual Space Tour at Base Q. I'm pleased to note that Japan and Switzerland have joined their scientific and industrial capabilities in space in various ways. We are partners on the ISS, are flying together on Bepi Colombo to Mercury, and our scientists are working jointly on the future CRISM and EarthCare missions. The next 4 days continue this joint ambition to explore and to inspire the next generation of researchers and explorers, as well as connect them to established research lab and industrial actors within our mutual space ecosystem. And as already highlighted by Mr. Reubi, the event is also about science communication and its contribution to enhance excellence in education and research. Ladies and gentlemen, international cooperation is essential in education, research, and innovation. I'm just grateful that the State Secretary for Education, Research, and Innovation is a partner to this event to promote the exchange of ideas and contribute to the promotion of science and education. And with that, I wish you a very successful event and would like to thank you.
Thank you very much, Mr. Krpoun. And then we would like to move on to the introduction of the creators of our outreach projects. First, I would like to call on Mr. Florian Cabot, Scientific Assistant, Laboratory of Astrophysics at EPFL, who has created the Virtual Reality Universe Project, VIRUP, for EPFL and the Swiss community. Thank you. Mr. Cabot, please turn on your camera.
Yes, hello everyone. Sorry, I won't have a camera today. We have some technical problems. I will share my presentation. So I'm Florian Cabot, software engineer at EPFL, and I'm here to talk about VIRUP, the Virtual Reality Universe Project. VIRUP is a visualization software targeted at outreach, and the main goal of VIRUP is really to show the different scales of the universe. So from the surface of Earth to the great cosmological structures, and to make them intuitive to the general public. We don't want to cheat with artistic views, so we want to be as accurate as possible with a lot of scientific data. So we think this software could also be a foundation for scientific visualization. So I'll show you a few features that we have in VIRUP. First, we have the cosmological scales visualization. This is the SDSS data. So it's observational data of galaxies. Each yellow dot you see here is a galaxy, and you can see a few examples of galaxies in the foreground. There are about 10 million galaxies in this picture. Another observational catalog is Gaia data. Here, all the background stars you see are from this catalog, and it also outlines the dust pattern of the Milky Way. There are about 1.5 billion stars in this catalog. We also show some simulated data. This is the Illustris-TNG simulation, which is a simulation of the cosmic web. So at each intersection of filaments you see on screen are galaxy clusters. We also have simulations of galaxies. This is a simulation of the Milky Way. And as you can see, we can render also volumetric data. Here, the red patches are gas, and you can see the dust that occludes the light of the stars near the center. About the data, we included a lot of catalogs and simulations, but the two biggest ones, I'd say, are the Gaia catalog, which, as I said, contains more than 1.5 billion stars, which accounts for about 35 gigabytes of data. And we also have the Illustris-TNG simulation, as I showed you, which contains more than 30 billion simulations particles, which is about half a terabyte of data. Of course, as you can imagine, including all this data into a virtual reality environment, which requires 90 frames per second and at least twice 1080p resolution is very challenging. In terms of memory consumption, you can't load everything at once. And also in terms of computation, there are no GPUs that can just render everything 19 times a second. So a lot of work has been done algorithmically to make this possible. The second great class of visualization we have are the planetary systems, starting with the exoplanets. Here you can see the Proxima Centauri star with two of its exoplanets, Proxima Centauri B and D. We have the whole exoplanetary, open exoplanet catalog, sorry, which includes 4,500 planets. And of course, we don't know what those planets look like, so we had to develop a way to generate those planets procedurally. As you can see, we have a few surface features of those planets and atmospheres also, which are procedurally generated. Of course, we don't need to procedurally generate the solar system because we know what it looks like. Here you can see Mars and one of its moons, Phobos. And the planets we know the best, of course, is the Earth. And in the background here, you can see the moon. This is actually the Earth-Moon configuration of today at this very time. Because in VRIP, you can put in a date and time, and the solar system will be visualized at this very date and time. We can do that because of the JPL Horizons tool from NASA, which gives very accurate positions for all kinds of objects in the solar system, including natural one, of course, but also man-made objects. The most famous one, of course, is the International Space Station. Here you can see it passing over Tokyo sometime in June this year. And we have a lot of different space probes. I chose to show this one, which is a Rosetta probe, which orbited the Churyumov comet back in 2013. There are a lot of means of interaction with VRIP. The main one is to use keyboard and VR controllers to roam across all scales without any visible loading time. But the vastness of the universe can be overwhelming for people. So for public presentations, we choose to have a predefined path and animations to show to people so that we have a smoother experience. We also collaborate with the Laboratory for Experimental Museology at EPFL, which has a lot of interesting hardware. And three of their installations are shown here, and we ported VRIP on them. On the top left, you can see their dome. On the top right, you can see the half cave. So it's basically two screens that are stereoscopic, one for the floor and one for the wall. And at the bottom, you can see their panorama, which is also stereoscopic, and it's a big 360 degrees screen. The last way of using VRIP is to use it to pre-render some movies. We released one last year for the EBOS press release on YouTube. And last month, we also released a 20 minutes movie, which is currently being shown on the Shinra Dome of the Science Museum of Tokyo. This movie will be released in October on YouTube. So if you want to see it before October, you can head to the Science Museum of Tokyo and watch it there. About the future plans of VRIP, the major future plan we have would be to integrate dynamics of the cosmological simulations we have. As you will see in the movie, we already have the data, but to render the movie, it took hours and hours. and we would like to try to show those animations in real-time VR, which is a great challenge. We have to stream terabytes of data through the headsets, so it will be a great challenge. In conclusion, I'd say we developed a powerful visualization tool for all kinds of astrophysical data because of its accuracy, and it was designed for outreach, but we think we can try to move on to scientific visualization with it. So thank you very much for your attention. Please get in touch. You can download VRIP on the website. As I said, there are movies that you can watch, and please try the live demo that will be available at the venue. Thank you very much.
Thank you very much, Mr. Cabot. It is really an amazing experience, and I hope all the guests today can experience the VR goggle version before going. Next, we have Mr. Alexandre de Montelau from Space at Your Service, EPFL.
So good morning, everybody from Switzerland, and good evening, everybody from Tokyo. I am so proud and honored to take part to such an event, this inaugural event of the EPFL Space Tour, which also means the launch of a project I've been working on with my association for almost a year now, Tranquility Base. So my name is Alexandre de Montelau. I am this year president of Space at Your Service, and I will present you Tranquility Base. Before everything, let me explain you quickly what is Space at Your Service. So we are an EPFL association recognized by EPFL. We are specialized in the promotion of space sciences in multiple ways to the general public and the student community. For projects in our events, we work a lot in collaboration with different stakeholders, such as EPFL Space Center, Space Innovation Laboratories, and government institutions, for example, for Tranquility Base. So I'm just gonna quickly show you some work from Space at Your Service. We are known on the campus for Astronomy on Tap. You can see on the left side how it looks like. The concept is the following. So it is an informal conference that takes place in a bar, and a speaker professional from the space field go on stage and talk about what he does. And after there is a big exchange with the public, and everybody has got a beer. So this is the concept. Maybe some of you has recognized him. This is Claude Nicollier, former Swiss astronaut, and he went at multiple of our events, Astronomy on Tap, and he will come back in the future. We also organize workshops for a young audience. We go into schools. This is what you can see on the top right. This is what we call Vivalis mission. And last but not least, what I will present to you today, Tranquility Base. If you want to know more about our station, don't hesitate to go to our website. We do other really cool projects. So before explaining what is Tranquility Base, I think it's important to say that this project is multidisciplinary because people from very different worlds were connected thanks to this project. We can count on laboratories, space-related entities, government institution, a video game studio, and at EPFL we were coordinated all this work in aim to create Tranquility Base. So this was such a good experience also in this way because we were dealing with people from very different work. So what is Tranquility Base? Well, Tranquility Base is an augmented reality multiplayer smartphone escape game on the theme of space. It is very specific, but the concept is pretty simple. You can see on the first picture on the left side, someone playing the game. So you can have a smartphone or tablet. It is a two-player game. So what you do is that you scan the ground with your smartphone, and after a virtual environment appear, and you can see exactly that the guy is playing the game, and through his screen he can see a virtual world. So it is, as I said, a two-player game that takes place on a lunar base and on a mission control center on Earth. So one person is on the lunar base, the other one is on the mission control center. And you can see on the right pictures, the top one, which is a view taken from a smartphone at the lunar base. And the bottom view is a view again from a smartphone taken from the mission control center. So the scenario is the following. A lunar earthquake has really badly damaged the lunar base. The oxygen is dropping down, and you have 20 minutes with a teammate to find a solution and save the mission. Tranquility base, why we did Tranquility base, but first, why it is so unique. So Tranquility base is a game, but it is a science communication tool never seen before, I would say, in the world. First of all, it is a multiplayer escape game, augmented reality on smartphones. So this is pretty unique. Also, Tranquility base the game contains current Swiss space research projects. I will come back to that later. Also, its scenario is based on real science. The purpose of Tranquility base, and this is also why we created this game, because we want to show through real research projects that are virtually present in the game what a lunar base in 2050 might look like. Also, we want to promote through this game Swiss contributions to the space field, because all research projects are from Swiss laboratories. And in this way, we want to show that Switzerland is a really strong space nation. And of course, give people knowledge about space. So let me now move on to the research projects that are present in the game. To make the long story short, we reached for laboratories and we asked them, so we wished for laboratories that were working on projects that were related to space. And we asked them if we could put a virtual version of what they are developing into our game and give them an application. So the first research project that is in our game is a modular origami robot called Morule from the Reconfigurable Robotic Lab at EPFL. The concept is the following. So they are developing these robots that have a triangle shape and that can fit together in the aim to create complex structures. And so the application we gave to these robogamis is that they are the shell of the lunar base, and this is what you can see on the top right from the lunar base. You can see triangles. These are modular origami robots that are fit together in the aim to create the shell of the lunar base. And on the bottom picture, you can see an isolated virtual version of Morule. The second research project that is in our game is Masahiro from the Thermomechanical Metallurgy Laboratory. What they do is that they extract the regolith, which is a rock present at the surface of the moon, and by extracting it with this rock, they can extract the oxygen that is in it. And the application we gave to this project is that actually Masahiro is the oxygen supply of the lunar base. They are using additive manufacturing processes. I won't go into details. It's still research projects, and there are still hidden stuff. Last but not least, Spacebach from Robotic System Lab at ETH Zurich. This is a crazy robot, and the goal is the following. The aim of this robot is to go to parts of the moon where no robots have never been because it was too hard for them. So it is very adaptive robots. And the application we give to this robot is, of course, Spacebach is the explorative robots of the lunar base. So I know that some of you have played the game, some of you not yet, but I will talk about hidden elements because this is also another way to communicate on space sciences. I'm going to reveal some of them, but not all of them. So after that, I let you play the game to find them, refine them, and also discover the new one. So I'm going to reveal some of them. So you can see on the left pictures, first one, some good luck peanuts that are present at every NASA launch. You can see on the middle picture a little Swiss cube. It was a satellite that was developed by I think it was 250 students, and was launched to space back in 2009. It was developed at EPFL. And on the right side, believe it or not, but there is a lightsaber, because back in the 90s, an astronaut brought a lightsaber from Star Wars movie into space. But there are much more hidden elements, much more things to know about space that are hidden in the game. So don't hesitate to take time to look and try to find all of them. What is the future of this game? So this game is made to evolve in the future. We really want to have more puzzles. From now, there are 3 puzzles. The game has a duration of about 20 minutes, but we would like to have, more puzzles, and of course, more research projects in it. We're already talking with the researchers that are working on projects I presented to you earlier. And we are talking about including the next version of what they are developing into our game, like the next version of Morule and the next version of Spacebach, for example. Our game will travel to Dubai World Expo in October 2021. So if you go there, don't hesitate to try the game. The game is already available in the App Store and Play Store, which means you can play at home. So please don't hesitate to tap Tranquility Base and aim to play at home. If you want to know more about Tranquility Base, go to our website page. There are everything I talked to you about, some more informations. And if you have any specific questions, please don't hesitate to contact me. I will be more than happy to answer your questions. And of course, last but not least, thank you to all our sponsors. It is crazy that a year after we have gone that far. And personally, I've never thought that, how to say it, like we exceeded what we were thinking of developing. I mean, the quality is even better of what we thought. And this is also thanks to you. It started as a little idea, and now it's a real project. So this is amazing. So thank you so much. Thank you, guys.
Thank you very much for the very comprehensive overview. As Mr. Alexandre de Montelau mentioned, the projects will be at the Swiss Next Mobile at the Swiss Pavilion at Dubai World Expo 2020, which opens in October. So if you are at the World Expo, or if you are going to the IAC, there will be also a chance to experience these projects in Dubai. So please stop by. Then, as we approach the latter half of our program, I'm very pleased to invite Professor Jean-Paul Kneib, Director of EPFL Space Center again, together with Professor Masahiro Takada, the KAVLI Institute for the Physics and Mathematics of the Universe, University of Tokyo, who will give a seamless presentation on understanding our universe from observational big data. Professor Kneib?
Yes. Okay, let me share my screen. Okay, so this is a joint presentation with Masahiro Takada, who is also online and with whom I've been collaborating in the last 10 years or so. And the topic of the talk here is about understanding our universe from observational big data. As it was kind of mentioned by Florian, we know a lot of the universe, but there's still a lot to discover. And my idea here is to explain a little bit what is the current research and current flow in the observation of the universe. And so my presentation will go on following this outline. I will say a few words about the universe. Then I explain how we are discovering more of the universe. And there will be two main parts, one about imaging, led by Masahiro, and one about spectroscopy that I will present. And then I will get a bit of the outlook. So you're all familiar with the night sky, and that's a picture that you can see here of the Milky Way. You essentially by eye only look at stars. There's effectively a few galaxies that you can witness by your eye, but mostly what you see on the night sky is a lot of stars. Stars of our Milky Way, our galaxy. There's about 100 billions of stars in our Milky Way. But there's in fact about 100 billions, if not more, galaxies in the universe. So really what we see by eye, it's only a very tiny part of the universe. And people, back in our history, they've been looking at the skies as you and me when you are in the remote places, looking at the sky. And of course, at first we didn't have any tool to really observe the universe. I mean, the only tool people had was their own eyes and maybe making some diagram on some paper. And that was about it. And so it was kind of difficult to grasp what was the universe. And I like this picture of an old document from the period of Copernicus, so about 500 years ago, where you see because of the study, the study of the sky, of the object moving in the night sky, essentially the planets, they kind of picture, what is the configuration of the universe. So they put the sun at the center, and around the sun, there's a number of planets orbiting the sun. That was already a revolution because beforehand, people were putting the Earth at the center of the universe. But then, looking more carefully, you can effectively decide that the sun has to be at the center, and then planets should turn around. And it's a good account of seeing the Earth on the third orbit after Mercury and Venus here. But when you think about it, these involve only very limited data. Just a couple of numbers can describe this universe. Today is a bit different. I mean, and this is kind of the view of our universe in 2000 or so, basically today. And this is just a snapshot of a numerical simulation. And what we see here is the cosmic web structure of the universe. Each point here is a galaxy. Each galaxy is made of 100 billions of stars, and there's about 100 billions of galaxies in the universe. And you see the pattern the very special pattern you can see in the simulation, but you can also observe with the current telescope. And you see those filaments, and these filaments are crossing at high density places where what we call are found cluster of galaxies, so concentration of galaxies. So to make this simulation, in fact, you only need a simple number of parameters, and of course the good theory behind that. And you can mimic, what you see in the universe with numerical simulations. But those simulations, of course, they're basically trying to match what we see. And so what we see are basically done through observation of the universe. And we will go through what we observe today. But before that, I want to give you the key theory that are explaining our universe. And this dated back from 100 years ago. Albert Einstein, a Swiss fellow, who described our universe in terms of the theory of general relativity. General relativity sometimes, seems like a very complex and mathematical theory, but in short, it's a very simple and intriguing theory, because it says that gravitation, so the force of gravitation, that basically link matter in the universe, is effectively the link between what we call the mass energy and the shape of the space-time. So basically, each time you have some mass in the universe, as we see in the picture here, it will distort space-time. Space-time is kind of a strange geometrical fabric of the universe. And each time you put mass somewhere, well, this fabric is distorted. And because it's distorted, it's also explained that, for example, the Earth is orbiting the sun, because locally around the sun, the space-time distorted. And instead of being flat, it's curved. And then the orbit of the sun, of the Earth around the sun, in fact, it's just a straight line in a curved universe. So that's exactly what Einstein wanted to say. And in fact, this has profound impact on our universe and how it evolves with time. And what I show also below, it's the simple Einstein equation. It's a compact form, and you don't have many details here. But what you can see, and I try to show, it's what are the components. There's a component about the gravitation, about the metric, the shape of the space-time, and the mass energy, which is basically the content of the universe. What is in the universe? So in the universe, we have mass, okay, matter, like we know around us, but there's also energy, which is a bit puzzling because that's something we don't fully grasp today. So after this theory, become and was, first, validated by observation, there's been a big growth because we develop big telescope, and with big telescope you can observe very far and you can observe the galaxies. And that was the work of Edwin Hubble in 1930s. And by looking at those galaxies, he could show that those galaxies are moving against our own galaxy. And he concluded that most galaxies were going away from us. And the only way to explain that is to say that the universe is expanding. In other words, you could say it's the fabric of space-time that I was just mentioning, the geometry of space is growing with time. And this is something it's very difficult for us to grasp because around the Earth, the geometry of Earth is quite static. I mean, it's not like your road, never get bigger. It's just there, it doesn't move. But the space and the space between galaxies is growing, and that's quite puzzling. But that means that in the past, the universe was smaller, it was denser. And that means maybe there was a time that everything was, so dense that, physics was a bit different. And that's what we call the origin of time. And that's what we call the concept of the Big Bang. So our view of the universe today is the following. We have here the mass energy content of the universe. So about 25%, 30% of the mass the mass energy content is mass. And this is made from atoms that you can discover through interaction with light. And there's also dark matter that you can only see because of the gravitational effect. And then there's 70% of what we call dark energy, which is something we still would like to understand better. So you see 95% of the mass energy budget of the universe is something which is unknown. And this is kind of the key motivation of astronomers today to investigate and to understand better. So let me give the floor now to Masahiro, who will tell us a bit more how we managed to get to these numbers. Masahiro. I think you're muted.
Sorry, so this is my part actually, or
yeah, I guess if you wish, you can start here, but otherwise I can take over.
Probably you could continue, so then
Okay.
I'll take over from Marcel's.
Okay.
Yeah.
Okay.
Please do that. Yeah, thank you. Sorry.
So that there's basically two key observation that led to this, distribution of mass energy in the universe. The first observation was the observation of what he called the cosmological microwave background. This is light coming from very far away in the universe when the universe was only 380,000 years old. So after the Big Bang. And this is a thermal relic emission. So the universe at that time was pretty hot, about 3000 Kelvin. Okay, and so it was radiating at some wavelengths, and because of the expansion of the universe, we can see that emission of light in the millimeter wavelength regime, so in radio waves. And what we see of the universe in radio waves 380,000 years after Big Bang is this picture. And what you see is there is some fluctuation in the distribution of the light, and red means it's warmer, blue means it's colder, and the difference in temperature is something like 10 to the minus 5 between different regions. And this tiny fluctuation, they will grow with time, and they will transform into the large-scale structure of the universe that we'll show a bit later. So what you see there is the seed of formation of matter structure that will come up and form galaxies and stars in the future. And that's from this observation that we managed to demonstrate that our universe is flat in the sense that we can use Euclidean metric to measure distance between 2 points in the universe. These has some consequences also on the value of the mass content and mass energy content I was discussing before. The other key observation that led to this distribution of mass and energy was a relatively recent observation that started 20 years ago and that was completed about 10 years ago in 2010, when we managed to measure 600 supernova of type 1a. Those are a very peculiar explosion of stars in the universe, and they can be used as standard candles. So because they have the same luminosity, and we can measure the brightness as a function of distance and as a function of the expansion of the universe. And that means we can measure how fast the universe is expanding. And when we do this observation, we can demonstrate, and you see the data points that we've been using for this demonstration, that the expansion of the universe is accelerating. But if the expansion of the universe is accelerating and we have a flat universe, it also means that our universe is made of like 28% of matter and 72% of energy, or dark energy, because we don't know what is this energy. So now we need to understand why we have such a universe and what it means. And so we need to understand what is the origin of the accelerated expansion of the universe. And there's different way to solve this problem. We could put this dark energy component as is the baseline, I would say. But what is this dark energy? I mean, energy for everyone, it's something that is created by something, right? But now in the universe it's there, and so where we can see it? What is the form of it? Okay, and what is the origin of the energy? So that's something we need to try to understand. You could also change the equation of Einstein, which it's just a model, right? But it means that you need to modify quite a bit the theory of gravity. Maybe there's a solution here. It's because gravity doesn't explain everything, but that's kind of difficult. So maybe that's a possibility. But okay, some people are reluctant to go in this direction. Another direction possibly is to say, well, you know, our fabric of the universe, our geometry is in fact a bit more complex than what we think. Maybe it has a fractal structure. And if you change the geometry, then maybe you can reconcile things, and then you can get rid of this energy, which is kind of a problem because we don't know its nature. So as of today, we don't have a good, simple, Unix theory solution of that. We lack of, you know, theoretical explanation, but the good thing is that we have the possibility to do more observations and to get more data. And that's what we call the precision cosmology. We want to do measurement to better than percent level. And to do that, basically, because our information is limited by data, we need better data and more data on the universe. So now let's turn the presentation to Masahiro.
Yeah, okay. So it's really great pleasure to be here. And I'm Masahiro Takada, working at the KAVLI IPMU. That's a building where I'm working at, KAVLI Institute for Physics and Mathematics of the Universe. So to study universe, we need both like physics and mathematics. And here I'd like to tell you about how we can use a big data to study a distribution dark matter. So I'm mainly working on this small telescope you can see in the picture. And this is at summit of Mauna Kea, 4,200 meter height in Hawaii Big Island. And this telescope is one of the really great telescopes in the world. And of course, Europe, including Switzerland, has many telescopes in the world. But here, Japan also has a big telescope in Hawaii, because Hawaii is one of the really great places for astronomical observations. One unique feature of this small telescope is this telescope has a prime focus unit. You can see this red circle. Thank you, Jean-Paul. Usually as a telescope has a secondary mirror in here, and then camera and the detector is, kind of behind the primary mirrors. However, small telescopes can have a prime focus instrument or camera and a spacecraft over there, because small telescope is kind of strong to fold such a big instrument at prime focus unit. So this means that this telescope is good for making a map of the universe. So in that sense, small telescope is really great telescope for mapping the universe. So could you go to the next slide, Jean-Paul? So KAVLI IPMU is leading a kind of big project, two projects. One is a hyper-spin imaging camera. The other prime focus spectrograph, spectroscopy. So then this HSC in short has a really, big digital camera, which has a 1 gigapixel. And this is international collaboration between Japan, Princeton University, and the scientists from Taiwan. This camera is already working very well. And then we are already using this camera to map the universe since 2014. Even we are still working on this camera for taking data from the universe. Also, we are working on another project, building another new instrument. This is a PFS. This is taking like a photon from all kind of objects, and to disperse a photon into the different wavelengths to take a spectroscopy. This is good for making 3D map of the universe, and maybe Jean-Paul will tell you more about. Again, this is going to prime focus unit. Again, this has a wide field of view is the area on the sky you can see at one time. And then this instrument can allow us to take a simultaneous spectroscopy of 2,400 objects one time. Even this is a bigger international collaboration between Japan and the US institutes, including Princeton, Caltech, and so on, Taiwan, Brazil, China, and the institute from France. I hope EPFL will join us as well. This means that because Subaru is the telescope in Japan, however, this international collaborator can put money, join into our project, which means that this project is really attractive for international partner to join. So could you go to the next slide? Indeed, Jean-Paul helped us. It's in the initial stage of this big kind of project for PFS. You can see Jean-Paul in the picture and me. So this is a first collaboration meeting for this PFS collaboration. already 10 years ago. That's a time flies. So, you can see various really famous professors in here, but, this is, kind of nature of internet project. Universe is, is for us. So everybody working on universe. So, all data is shared by everyone. So Hyperline Spring-Cam HSC imaging survey, we are currently working on our actual data. So then this is ever largest program with our telescope, and spending 313 nights. And then we are already taking data. Already our data is 500 terabytes, and we already have like a 5.5 billion objects, galaxy and stars, and will be completed this survey project within this year. So this is quite exciting, big data, and this is going to be public. So this is exciting. So how to measure dark matter distribution? So one way to do that is a weak gravitational lensing effect. Again, this is a prediction by Einstein gravity theory, as Jean-Paul nicely described. Einstein theory tells if there is a matter in the universe, matter kind of bent space-time, so even photon cannot travel straight. The kind of path of light emitted from distant galaxy is bent by foreground dark matter. As a result, we can see a distorted image in the galaxies. So light picture showing that this is a kind of obvious example, but blue galaxy in the background galaxy behind these orange galaxies. This region is we call a cluster of galaxy regions, is some particular place where dark matter is really concentrated. So this gravity, cause a distortion in the background galaxy images. In other words, if you can observe distortion in background galaxy images, you can infer how much matter is there. It turns out you need lots of invisible matter, which is called dark matter. So we know dark matter should be there. So could you go to the next slide, Jean-Paul? Yeah. Then we are using data from solar telescope. This is actual data, and we use that data to make our largest map of dark matter distribution universe. This is a blue contour showing that dark matter distribution universe by using 10 million galaxies images from Subaru. Orange region showing that distribution galaxies. You can see galaxy indeed formed in a place where dark matter more concentrated. This is a prediction from current structure formation paradigm. Indeed, our data is proving dark matter is really driving force of our cosmic structure formations. So this is why we know why we need dark matter in the universe, how to measure it. Okay, Jean-Paul, could you take over?
Yes, and so that's the current project. And there's going to be a new project, which is called Euclid, which will do the same thing as the hyper-supreme camera on the Subaru telescope, but from space. And that space mission, Euclid, is going to be launched in basically end of next year, beginning of 2023. And it will do something like the HSC, but it will also, using the weak lensing technique, but it will also do the galaxy clustering. And let me maybe explain a bit what is galaxy clustering. When we look at the universe, and that's the map of the universe that we see from the cosmological microwave background, so the very early time of the universe, the precision at which we're measuring the fluctuation is something like 0.1%. Today, when we look around us, we see galaxies. And the same fluctuation we see in the CMB can be seen also in the galaxy distribution. And so if we manage to make the link between the size of the fluctuation in the CMB map and size of fluctuation of overdensity of galaxy in our universe, it's probably one of the best way to measure very precisely the expansion of the universe. So here we're not mapping dark matter, we're mapping galaxies in 3D. And from the way the expansion of the universe is measured, we can deduce the dark energy constraint. And how we do that? We do spectroscopy. And that's basically like the project of the PFS that will be started in a couple of years at Subaru. But up to now, we've been using the Sloan telescope that is here. And we use this plate in aluminum, where we put a design fiber, we find design holes, and then some people would put fiber opticals in those holes. And then we observe each galaxy light that will go through the fiber into a spectrograph, and then we can measure what we call the redshift. When we know the position of the galaxy in the universe in 3 dimensions, because that's basically what spectroscopy is telling us, and here is part of the movie of the VIRUP visualization effort. We can compute the distance between 2 galaxies, and we can basically count the number of galaxies with a given distance. Then you do a Fourier transform of this distribution, and that basically gives you what we have on this plot that we call the power spectrum. It's a bit of a complex mathematics, but what is important to understand is that in the shape of the galaxy of the data point we measure, we'll have some imprint of what is the theoretical prescription of all our universe is growing with time. And that means we can measure dark energy, we can measure also the type of dark matter, and we can see how it grows with time. And that's the final measurement of SDSS. And what you see in the background here is the CMB light. And what you see in the middle here are the distribution of galaxies as a function of their redshift. The color is just a measure of the distance and the type of galaxies. And what we're measuring on the left here is some numbers. You can see some numbers that are corresponding to the development of the structure in the universe. So to reach this measurement, you need a lot of galaxies, a lot of measurements. And the SDSS project, which is kind of finished last year, and we made this first movie visualization data, has in total something like 4 million objects. And the next project in which I'm working is called the DAISY project. And the target is by basically multiplying by 10 the number of objects in our catalog. So how are we going to do that? We have built with an international team across the world an instrument made of 5,000 robotic eyes that you can see here. And so what are these robotic systems? Those robotic systems are basically trying to replace our system with the plate and with fiber optics. And each fiber optic is controlled by these, what we call fiber robot positioner. And in the fiber robot positioner, there's 2 motors. And in fact, the motor made in Japan from the Namiki company, very competent company, being able to build small motors. The motors are 4 millimeter diameter. And there's the best motors of this size available. So working with Japanese to make this project, we aim to discover more of the universe, 30 millions of objects. So that's the plan for the next future. There's many projects. I mentioned DAISY, I mentioned Euclid, Masahiro mentioned PFS, but there's more projects to come because technology will enable us to do that. And to finish, I want to mention the SK Observatory, which is this radio telescope project. The project aims to observe the universe in radio frequencies. So typically between 50 gigahertz and 50 gigahertz and 50 megahertz. And there will be two sites, one in South Africa, one in Australia, because those are the best place to put a radio telescope. And we will discover even more the universe closer to the Big Bang, probably reaching 1 billion measurement in terms of 3D position of galaxies. And this is truly a big data project, because the forecast is that it will produce 700 petabytes of data per year. So that's the big challenge for astronomy and understanding universe, is to basically, be able to digest this big data. As I just say, the volume of data expected is about hundreds of petabytes by 2027. This will allow us to map very precisely the dark matter in the universe using Euclid and the radio telescope. We will be also able to measure the 3D map of galaxy in the universe. That's allow us to trace the large-scale structure that you can see in the Variable movie. And there's many projects that will do that. But what I'm concentrating also today is to develop data science, because we will need data science to digest all these data that are coming from our telescope. And that will allow to understand better the universe, in particular the dark matter and the dark energy problem. Just to recap in terms of volume of data, hundreds of petabytes a year. It's also, if you compare to Google, it's what the type of data Google is using on a daily basis. They're basically processing 20 petabytes a year. So just to give you the scale, I mean, we're getting into a regime where the data from the universe is kind of similar in size that the whole world is using on a daily basis. And so that's a challenge. That's a challenge for us astronomers, but in fact, it's a challenge that is faced by our society. And because we're gonna help in trying to find solution, maybe some of the solution will also benefit our society. So not only we'll learn about the universe, but we make our life better, hopefully. Okay, thanks. I'm very happy to receive any question if there are.
Thank you very much, Professor Kneib and Professor Takada. May I ask for a question from the Tokyo venue, perhaps? If there are any? It was a very in-depth question. Excuse me. It was a very in-depth presentation, and I believe we are trying to absorb the terabyte data that was also in the presented. But I actually, looking at the presentation, I was very impressed that in the outreach program of the VIRUP, that I felt the very basics of the presentation that you have presented were also shown in VIRUP. So this was something that I would like to also, if anyone hasn't yet watched the VIRUP movie or the one that will be uploaded very soon, this is very much the entrance point, I can assure everyone, to these more academic and more even more interesting researches. Since we do not seem to be able to catch up to the in-depth, may I ask actually the I think Professor Kneib, you mentioned the next challenges, but are there any concrete projects that you can share with us, perhaps, that you will be joining with Professor Takada?
Well, I guess the challenge in the coming years, and that's hopefully, we will attack the problem with Masahiro or Takada, is this mapping of the universe in 3D. What we have been able to measure with the Sloan data up to now is basically we managed to confirm observation that are basically were guessed with the CMB observation and with the supernova observation. So we kind of confirm the results, and now the next step is to go a bit behind. And thanks to the DAISY project and the PFS project, I think we're gonna be getting data which will probably going to give us a puzzle, because it will be so accurate that likely any of the current model of that are described in our universe will not work. And we start to see that with some current tension between some parameters we are deducing for the expansion of the universe. The measurement of the expansion that is done locally and that is done using the CMB information are not really in agreement. And so with PFS data and with the DAISY data that are going to come very shortly, hopefully we will be able to have the data, the ingredients that will help us solve the problem. And that has possible consequences on our understanding of the very early universe or basically the shape of our universe, just as two possible directions. But maybe the explanation will be a third direction. So this is really science in action that will happen in the coming years, maybe 2-3 years from now.
Thank you very much. That sounds like a very short term when we are talking about the universe.
Yes. I don't know if Masahiro want to add something.
No, you nicely described. Yeah, dark matter is such a mysterious component. It's really shame for us. We don't know anything about it. So we really need big data to understand what those are. So then hopefully in a few years we can tell what those are. That's our goal. So we need more data to tackle.
Thank you very much. Now, may I invite the online guests to, if they have a question, to please, or make a statement, of course, please raise your hand in the Zoom function found on the button of your Zoom window under reactions. Thank you. Mr. Vincent Durand, please unmute and make your question.
Yes, hello.
Thank you.
Hello, everyone. I would like to thank all the speakers for the event. That was really amazing. I have a question for Professor Kneib and Professor Takada. You mentioned that indeed astronomy has to rely on data science in order to pursue with those projects. Are there any projects so far about developing data science, maybe as a discipline that is taught in an academical way, or other projects with interdisciplinary projects about that?
Masahiro, you want to?
No, let me think about it. It's indeed these days, like data science or machine learning or artificial intelligence, AI, are getting very important, very common, and very powerful to analyze our data set. So in that sense, is like University of Tokyo has launched new project between SoftBank. SoftBank is the biggest cellular phone company in Japan, and the University of Tokyo to develop a new initiative between Tokyo and the company to develop a new technique using machine learning AI. And that new institute, you have a physicist, data scientist, computer scientist, even some people, some professor from kind of medical institute and so on. So those all these days that we are talking about a really big data set to handle our each one's program to kind of extract full information from those data sets to understand what's going on. So in that sense, now I would say boundary is not there. Even if I'm working in universe, but then maybe our problem might be common. How we can deal with such a big data that in that sense, now we are beginning to start to various people for new technique, new approach. That's machine learning AI is a kind of one key concept in this academia field. I don't know, is a jump or maybe you can add. What do you think?
I think effectively AI, machine learning are techniques that are being moving from computer science to astronomy and astrophysics, and we are trying to use them more regularly, and we're also trying to put some physics in these techniques, which are kind of just phenomenological development at the beginning, at least. So there's some very interesting development in trying to put more physics in machine learning techniques. And also what I wanted to maybe add, and that's something we're trying to develop, is developing with the computer science community ways to adapt software that deal with big data, not just to run on normal CPU, but to run on these graphical processor unit, these GPUs that are much faster, but of course they can only do very simple processing of the data. So you basically have to modify and adapt the complex software we're using, and we're doing that with computer science, and I'm sure there's also very much some synergy development with computer science to adapt and push the GPU processor to be more powerful.
Thank you so much for your answers.
Thank you very much. I was hoping to also invite some questions for Mr. Cabot for VIRUP and Mr. de Montelau for Tranquility base. However, since we are a little bit quite over our time, I would invite everyone to visit our website, EPFL Virtual Space Tour.com. There is a contact email address. So our speakers, I would believe, will be happy to answer your questions if you have any. I would also like to stress that we have 3 more days of events. The latter 2 on the 17th of Friday and 18th of Saturday will be at Tokyo Midtown Hibiya. And it is a public event, so we would very much welcome you to join us there, if not for the demo, but also for very exciting talk events. So in this case, I would like to again thank you very much, all the speakers and all our guests for joining us today, and wish you all a very nice day and evening.
Thanks so much.
Thank you.
Thank you so much.
Thank you very much. Bye-bye.